Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 28, and we are going into chapter 3, continuous distributions, part 1. Last time we discussed in the last section the Poisson distribution, and specifically in the last video we talked about some examples. We also did an example for the approximation of the Poisson for the binomial distribution. This time we're going to look at these continuous distributions, not a discrete distribution. We're going to talk about the differences, the cumulative distribution function, and now instead of a PMF, which is a probability mass function, we're going to talk about a probability distribution function. And we're going to give an example of the uniform distribution, look at expected value, variance, and the MGF. We're going to do a supplementary or a supplemental video next that will be the continuous uniform distribution, and in the last video for this section we will look into percentiles, quartiles, and do some examples. So we're going to let X denote the outcome when a point is selected at random from an interval AB, okay, and where A and B are finite, and we want to perform this experiment so that the probability that a point is selected from an interval A up to X, where X is between A and B, is proportional to the distance of X from A relative to the distance of B to A, from B to A. So is proportional to the length of that interval. So what we end up with for the CDF is, and the CDFs, capital F of X, need to be written as piecewise functions. So you always need three parts to it. The first part is where it's 0, and that's going to be below the support of X. So, and then the equation for the PDF in the support of X, and then the fact that it's 1 as when X is at the maximum value of the support and above. So this, what we've described here is called the uniform, continuous uniform distribution. And so here is the CDF of that. And you'll notice here is 1. And our support starts at A, ends at B. And then you'll see that it goes up evenly from A to B. Anywhere that's below A, it's 0. Anywhere it's above B, it's 1. And if you remember, CDFs have the property that the limit as x goes to negative infinity of f of x equals 0, and the limit as x goes to positive infinity of f of x is equal to 1. We learned that back in chapter 2. So we can look at, we can describe f of x as the integral, so of f of t dt from negative infinity up to x. And in this case we have 1 over b minus a from a, b minus a dt. So remember that we have to use a different variable here if we're going to have x in the limits. We can't differentiate or integrate x and then up to a value of x, because x is changing in that case. So we need a different variable, and we're treating x as a constant here, even though that constant can take on different values after we determine the expression. Okay. So in other words, we take the derivative of f of x, and we get capital F of x, and we get little f of x. And this is, if you do take this quantity and take the derivative, you will see that you get this, okay, for x between a and b, and 0 otherwise, right? And if we graph this PDF, then we'll see that in order to have an area of 1 here, so an area under the curve of 1, then this is a rectangle, and we could call this P, And so if this area is 1, then this length is b minus a. So b minus a times p equals 1, so p equals 1 over b minus a, using what we know about rectangles. But instead of just using what we know about rectangles, that works in this simple case. It doesn't work when the PDF is of a complex form, which we're going to study. So we'll need to use calculus. And that's why we've given the CDF as an expression of an integral of the PDF. Okay, so this is the expression in general that we need to know. So as I mentioned before, this PDF and the CDF given are those of the continuous uniform distribution. It's also called the rectangular distribution, which you can see if you draw the lines there. Okay. And to conclude, f of x is the derivative of the CDF. Now, if you notice, the CDF does not exist at x equals a, x equals b. You say, well, why not? Well, look at this and you'll see that in this direction, the derivative would be 0. And from this direction, it would be x, 1, right? So, and then up here, the same, this would be 0 coming in from this direction and 1 coming in from this direction. So, since those limits don't match up, the derivative does not exist. Okay. But since f of x is continuous, it turns out we can't assign probability to an individual points. Well, why not? Well, if we look at this definition, if I want just a point, if I draw the picture of the PDF, if I just want this area at a point, say x, then that's going to be from x, well, let me call it something besides x. Let me call it a. Then the integral from a to a of f of x dx is equal to f of a minus f of a, which is going to equal 0. Okay? There is no area. So area and probability are synonymous in this section where we talk about continuous random variables. So where area is equivalent to probability. And so this is a concept you need to quickly grasp to be able to do these types of problems easily. All right. A PDF of a continuous type random variable has to satisfy the following. So just like a PMF, f of x has to be positive for all values of x, 0 or greater, for all values of x in the support of s. And if we integrate over the support of x, I said the support of s, I meant the support of x. If we integrate over the support of x, f of x dx, that has to be equal to 1. This is similar to the requirement that the PMF, the sum over the x's support, has to be equal to 1. Now, what is not true, it's not true that f of x is not equal to the probability that x equals x. In fact, this quantity, as I just mentioned, is 0, and it's always 0 for any value of x. Again, we could go back to this right here where we showed that. So if a and b, the interval ab, is contained in the support of x, then the probability that x is between a and b is given by this, which is also, by the fundamental theorem of calculus, f of b minus f of a, the CDF. Okay. We call f of x the cumulative distribution function, and confusingly, it is also called just the distribution function. So we have the probability distribution function, we have the cumulative distribution function, and the cumulative distribution function is sometimes just called the distribution function of random variable x. So if you just see distribution function, think CDF. Okay? And the CDF is the same as it was for the concept is the same as it was for the discrete case. It is the probability that x is less than or equal to some value of x, but it is now, instead of a summation, an integral. Okay? And we're showing x being anywhere from negative infinity to positive infinity, but that doesn't mean the support of x is from negative infinity to positive infinity. This covers the general case. Now let's talk about the expected value of x. This again is analogous to the discrete case, but now instead of a summation, we have an integral over the space of x. So it's still x f of x dx. And if you remember your Riemann sums, an integral is a sum of those infinitesimals, so to speak. So, we can rewrite s as negative infinity to positive infinity, and so the integral of x f of x dx is e of x. It's also mu. So as you should know from the discrete case, the expected value of a function of x, instead of putting x here, we put the function g of x here. So it's still f of x dx. So whatever is here goes in the front here. Okay? Just like we did in the discrete case, except now again it's an integral. It's still true that the variance of x is the expected value of x minus mu quantity squared, which is ex squared minus ex quantity squared. You can show this with the integrals. I'm not going to, but it's very easy to show. And here's another expression for the variance, and then directly here is the expression, the integral expression for the variance, x minus mu squared f of x dx. So remember that this goes here. What we're taking the expectation of goes in front of f of x dx in the integral. And of course, the standard deviation is going to be the positive of the square root of the variance. The moment generating function, likewise, is very similar to the discrete case. So we have m of t is equal to e of the expected value of e to the tx. And again, we put e to the tx into our integral in front of f of x dx. And now we have to define t, this range of values for which this is true or converges. And it's still true that we have the derivative at 0 of the mgf is mu, and the second derivative calculated at 0 is ex squared, and so forth, if they exist. And that is also a big case. We're going to run into cases where they do not exist in the continuous case. So here's a very important remark. In both the discrete and continuous cases, if the rth moment exists and is finite, then all the lower moments exist and are finite. In other words, if e raised to the if e of x to the k exists and is finite, then that's going to be true if e of x to the r is exist and is finite. Then e of x to the k, where k goes up to from 1 up to r minus 1, those are also existing and finite. The converse is not true. Okay? E of x can exist, be finite, but it is not true that ex squared has to exist, much less be finite, if it does exist. Okay? If the moment generating function exists and is finite for this value of h, this region of t, around some area or some neighborhood, then all the moments exist and are finite around that neighborhood. But again, the converse does not have to be true. So those moments can exist, but that doesn't mean that this function, the moment generating function, exists. All right. So that is the end of this lecture. Don't forget to scan and upload your lecture notes before midnight at the date listed on the course calendar. You'll want to update your list of definitions, or distributions, I'm sorry. You may want to update some of your facts with that remark that we went over. If you have questions, come to virtual office hours. If you can't, then email me. Again, send me a picture of the problem, send me a picture of your work. I'll be able to help you through email that way. And so I hope you will take care of yourself, and we will see you next time.